morning everyone, this is Hazel Mempin, and for today we will talk about the blackbody radiation. In 1800s, mankind had discovered that objects made out of graphite with soot or lamp black produce a very unusual type of light. These objects were very different in any other objects, and they became known as the blackbodies. A blackbody is a theoretical object that absorbs 100% of the radiation that hits it. Therefore, it reflects no radiation and appears perfectly black. As a result, the type of light that was produced was called the blackbody radiation. If 100% of the radiation occurring on an object is absorbed, it is called a perfect blackbody. The absorption coefficient of such an object is 100%. In a ideal case, a blackbody can absorb the radiation of all types of wavelengths. Carbon black is an object that can absorb 99% of the incident radiation. So whenever radiation is absorbed by a blackbody, due to this absorption, the temperature of the body also increases. As a result, the temperature of that body increases in the comparison to its surroundings. In this condition, the blackbody starts emitting radiation. This radiation is called the blackbody radiation. This is not only done by blackbody. Rather, when any object absorbs radiation, it starts emitting radiation itself due to the temperature being increased. So any object emits radiation due to the increment in temperature, then this radiation is called the blackbody radiation. Our sun is a perfect example of blackbody because it emits radiation of all types of wavelength. Scientists made a blackbody in the lab that could absorb up to 99.9% of the radiation. For this, a hollow sphere was taken which has a narrow hole. The inner surface of the sphere is coated with carbon black. When the radiation comes inside through this narrow hole, the radiation hits the wall of the sphere and gets absorbed by 99%. The remaining radiation reflects back and collides with the wall again. In this way, in each collision, 99% of the radiation is absorbed. Due to the absorption of radiation, its temperature also increases. As a result of this, it starts emitting radiation from the narrow hole, in which all wavelengths are present. This radiation is called the blackbody radiation. The horizontal axis represents wavelength of the light emitted in nanometer, which is 1 billionth of a meter. The vertical axis represents intensity. As the temperature of the blackbody is increased, the emitted light changes in a predictable manner. The position of the maximal ignition moves to a shorter wavelength. This observation was formulated into a law by William Wien in 1896, which is known as Wien's displacement law. It states that the product of the maximum wavelength for the emission times the temperature always equal a constant B known as the Wien's displacement constant. In 1879, Joseph Stefan discovered something else about the blackbody radiation. The area under the curve is equal to another constant, which is sigma times the temperature to the fourth power. This became known as Stefan's law, and the sigma is known as the Stefan-Boltzmann constant. An early classical attempt to explain blackbody radiation was the Rayleigh-Jeans law by Lord Rayleigh and James Jeans. At a long wavelength, the law matched experimental results very well. At a short wavelength, there was a major disagreement between the Rayleigh-Jeans law and experiment. This mismatch became known as ultraviolet catastrophe. The ultraviolet catastrophe, also called the Rayleigh-Jeans catastrophe, was the prediction of the late 19th century classical physics that an ideal blackbody at thermal equilibrium will emit radiation in all frequency ranges, emitting more energy as the frequency increases. But it was not until Max Planck came along in 1901 that the full equation for the blackbody radiation was formulated. Planck introduced the concept of quantum of action. 1918, he was awarded the Nobel Prize for the discovery of the quantized nature of energy. He assumed that the cavity radiation came from the atomic oscillation in the cavity walls. Planck made two assumptions about the nature of oscillations in the cavity walls. Planck's first assumption is that the energy of an oscillator can have only certain discrete values of energy. Energy is equals to N times H times F. N is a positive integer called the quantum number. F is the frequency of the oscillation, and H is the Planck's constant. This says that the energy is quantized. Each discrete energy value corresponds to a different quantum state. Planck's second assumption is that oscillators emit or absorbs energy when making a transition from one quantum state to another. The entire energy difference between the initial and final states in the transition is emitted or absorbed as a single quantum of radiation. An oscillator emits or absorbs energy only when it changes quantum states. The energy carried by the quantum of radiation is energy is equals to H, which is the Planck's constant times frequency. The significance of Planck constant is in this context is that radiation such as light is emitted, transmitted, and absorbed in discrete energy packets or quanta, determined by the frequency of the radiation and the value of Planck's constant. The energy E of each quantum or each photon equal Planck constant H times the radiation frequency symbolizes the Greek letter nu or V, or simply E is equals to H times nu. Planck became known as the father of modern physics because Planck's law introduced the concept of quantum, and the field of quantum mechanics was born. And that's the end of the video. Thank you for watching.